Hello everyone, my name is Luca Bianconi and I give the speech on behalf of Gruppo SIGLA and of other partners involved, Italian CNR and Flairbit company. I present here a work performed as part of PICAP project, implementing a case study where an Internet of Things infrastructure has been designed, created and used as a base for the provision of smart services for smart cities. Gruppo SIGLA acted as PICAP project coordinator. It is an Italian consultancy firm, recently became part of the Relatec group devoted to information technology and industrial automation. The company provides consultancy and system integration services, working mostly with large enterprises, with operations on global scales. Through its research and development team, since 15 years, Gruppo SIGLA is committed to innovation. In this sense, it works on funded projects, European and Italian ones. PICAP project, whose work is in part presented here, is one of those latter, Italian projects. The company collaborates actively with other industrial and research entities on several domains. In particular, it is worthy to quote cybersecurity, information technology, e-health, energy, Industry 4.0 and environment. There are two initiatives useful to quote in this context because strictly related to the use cases presented today. They are, first, the CyberTooth Joint Lab on cybersecurity, mostly focusing on challenges of the Internet of Things, funded together with University of Padova and Genova. Second, the so-called SIGLab, that is the laboratory on the Internet of Things internal to the company, created initially to experiment PICAP investigated topics and evolved furtherly in the months after the project. In line with all this story, it needs to underline PICAP project is a project, indeed, funded through the Italian region of Liguria, and it aimed at implementing and validating innovative methods and tools for the energy and environmental management of urban districts, considering as main target of urban managers of our cities. Considering this mission, the project involved several technologies around the Internet of Things world, namely sensor networks, cloud and fog computing, system architectures, artificial intelligence, machine learning, and data science. The activities of the project covered multiple objectives and elements, executed by a large consortium of 5 industrial partners and 2 research entities. The use case presented here, though, focuses on a specific part of the whole work to be in line with the topics of today's event. The use case implementation involved then a smaller work group consisting of 3 partners: Italian CNR as research entity, first of all, secondly, Flairbit, an Italian small-medium enterprise working actively on cutting-edge IoT applications, and last but not least, of course, Gruppo SIGLA, an Italian enterprise coordinating the project and presenting this speech. This use case presents a specific set of aims, in particular through the setup of an Internet of Things system guaranteeing the quality of indoor and outdoor environments for citizens to produce their well-being and prevent their exposure to dangerous pollutants, or to prevent the sick building syndrome. Moreover, to pave the way to enact energy savings in smart buildings and to pursue higher standards in matter of quality of life and smart city. Not last, it wants to experiment performances of the selected Internet of Things sensors technologies. For the use case, an Internet of Things network was designed and developed involving 2 buildings of the Italian city of Savona. It wanted to assess energy efficiency and well-being of occupants of a police station and of the outdoor air quality of a school's area in the city center of Savona. The network was required to be designed as distributed on different building areas and to be affordable without compromising the quality of efficient monitoring and data collection. Adoption of wireless sensors to avoid heavy infrastructural works and low-powered wide area networks in particular was the choice performed by the authors. LoRa, in particular, appeared as an optimal solution for the implementation of monitoring infrastructure, in line with the requirements expressed in the first phase of the pickup project for reaching the expected objectives that can be summarized as the capability of being a sustainable solution under economical and operational terms. The architecture of these infrastructures wants to experiment and deploy a fog computing architectural pattern for the implementation of different Internet of Things aspects. It includes all the three layers of a fog architectural pattern. Firstly, the edge layer, including sensors installed on the 2 involved buildings, mostly to collect data, but also including some actuators, mostly to switch on and off appliances. Secondly, the fog layer, consisting in fog nodes deployed on each building to deliver local computing and storage resources, and acting as proxy for the data from the sensors to the servers. They has also the responsibility of guaranteeing the remote access to the node for performing monitoring and maintenance operations. These features proved to be very useful, for instance, during the pandemic's harsher periods, to guarantee the operational continuity without putting maintainers at risk. Thirdly, we have the cloud layer that receives all the data collected by all the pilot sites and provide services to the users, such as user interfaces and dashboards, to control and monitor data and infrastructural elements. The pickup project designed and installed then 2 infrastructures onto the 2 buildings that were involved into the experimentations, respecting, in any case, this architectural schema, even though the objectives and buildings were different under several aspects. Some details and differences are presented now. The first building and use case wanted to assess the possibility of efficiently monitoring indoor air quality and comfort for the police station building of the city of Savona in Liguria, Italy. The edge layer consisted of a set of LoRaWAN sensors to collect data on temperature, humidity, luminosity, air quality. The fog layer consisted of a so-called fog node. This latter is made of a Raspberry Pi and of a LoRaWAN gateway, put in communication and integrated to exchange and control data and to communicate with a remote cloud server. The cloud server represents the cloud layer. It receives all the data from the LoRa sensors to be furtherly elaborated and to provide smart services. It consists, first of all, of a LoRa server built over the open source Chirp Stack project and including other software elements provided by the partners involved. In the use case presented, for instance, the sensitivity product for Internet of Things provided by one of the authors, Flairbit. For sake of completeness in the presentation of the architectural fabric deployed on the two building sites, it needs to add the second use case aims at assessing the outdoor air quality in the areas surrounding schools in the very center of the city of Savona. The infrastructure deployed is very similar, but for what relates the edge layer. It consists in outdoor air quality LoRaWAN sensors, monitoring temperature, humidity, and presence of polluting materials. The pickup project lasted for more than 2 years, and demonstration and test campaign covered several months of continuous data collection. It allowed to reach some results on different aspects, carefully executed with the crucial scientific and technical support of CNR colleagues of 2 Genova departments. First of all, it allowed to perform an evaluation of the LoRaWAN-based network infrastructure's efficiency that gave satisfying results in terms of effectiveness, of communication quality, and replicability. The evaluation is based on the collection of communication parameters such as strength of signal, signal-to-noise ratio, payload, and times analysis, as well as the correlation of performance metrics. A second interesting result consisted in the possibility of performing environmental evaluations based initially on the occupancy assessment of different areas of the buildings, to be used for producing insights and policies, and to design policies to reduce energy demand and increase comfort for occupants. Third result expressed by the use case experimentations is the evaluation of air quality in the indoor and outdoor environments for areas of public interest, all that controlling CO2, VOC, and PM values along several monitoring months. This work wants then to let the urban and building managers to have useful data to increase the life quality and, less in general, the comfort for citizens and building occupants. The use cases presented in short in this session focused on a specific aspect of the pickup project that refers almost entirely to its Internet of Things elements, and in particular to the implementation of the network infrastructure based indeed on LoRaWAN technologies and involving the setup of a complete full-stack architecture from edge to cloud and including fog elements. The overall experience produced interesting evidences for the authors, CNR, Flairbit, and Gruppo SIGLA. Just to recap, it indicates how it can be easily used for performing several tasks to monitor in the long term smart cities aspects. Secondly, to quickly introduce actuation elements where needed and possible. Then, most of all, to have characters allowing its easy replication and to scale introducing new elements, sensors or so, for instance. Then, to provide the solution designer the possibility to create services based on its monitoring and actuation features. Last but not least, the project and the experience presented here as a whole, represented for the authors to be a foundational experience for progressing the adoption and investigations of the topics touched. First of all, low-powered wide area networks and Internet of Things architecture design. Thanks a lot for your attention.